Forgot to do that in my last class. So this whole session, what I'm writing on my screen, what I'm saying, my video will all be recorded, and then I'll post it in what I'm referring to as the class lecture videos. So if you click on that, it'll take you to my YouTube channel. And right now it's just an empty playlist except for the introduction video, but things will start to appear there day 1, day 2. So just keep that in mind. Everything I'm writing down, you can always go back and access that later, all right? And then we have our homework solution videos. This is very useful. Pretty much every homework problem that I've assigned, I'd say 98% of them, I have the solutions, me standing up in front of a whiteboard working out the problems. So it's kind of worth noting here how long these homework assignments took me. You know, I don't think there are really any assignments that are under an hour. Some of them are up to 2-3 hours. And that's me actually working through the problem. So it's kind of like, you know, I know which way I'm supposed to go with each problem. So you should anticipate a lot of time needed to get the homework done. And then I have old lecture videos. If something happens like Zoom crashes and we can't meet one day, most likely what I'm going to do is email you and I'll send you a link to a video, and it's probably from a past semester where I'm covering the material that we were supposed to cover. So if you want to, you could go click on that right now and you could actually get a little bit ahead in the class by watching material ahead of time, all right? The syllabus, and I don't want to go through all this because I already did the course introduction. The main thing here is me talking about my office hours. So right before this class, I had office hours from 11 to 12:30. So if you ever want to come and just ask questions, I'm available. And then on Monday, Wednesday, I'm also available at 2 different times. So just read through this. As far as what you need for the class, by enrolling in this class, everyone already paid for access to an electronic version of the book. So you do not need a physical copy of the book. So let's do a quick poll, because I asked my other class the same thing. How many of you have a hard copy of the book? Right? How many of you actually have the physical textbook for the class? All right. Wow, okay. So that's, most of you don't, all right? Most of you don't. So if you do have the book, then you could, if you want, just work through the schedule, do the pages out of the book. There's only 3 of you that would apply to. Everyone else is going to have to get access to the electronic version of the book. So to do that, you're going to need to click on this link, and you're going to need to type in this. This is called the class key. So I'll just show you real quick. You click on that, and then right here, enter class key, or you can put up here in the right corner, enroll in with class key. Click on that, put in the class key, and that should get you into the class, all right? And then let me go ahead and take you in there, and I'm going to show you kind of what it looks like, just so you are familiar with it and you know where things are. So let me find your class first. Okay, so this is what it's going to look like for you. All right, so the main things for you to know about this website here is that on the bottom right-hand corner, you will see the textbook. If you click on that, you will have access to all the pages out of the textbook. So let's say that you want to do your homework, right? And you bring up that calendar, and we're covering 3-5 today. You're supposed to do page 181. You're supposed to do these problems. What you're most concerned about here is what problems to do, numbers 1, 5, 15, 16 through 28, and what section, so 3.5. So what you would do is go to the book, go to chapter 3, Let's see what happens here. It remembered where I was last time, but you would have to navigate to 3.5, the exercises, which are at the end of the, so it's like, here's the textbook, here's the information. At the end of that section, you will have your homework problems. Where'd it go?
And Professor, as far as the homework, do we have a week to complete it? Do we have a few days? How do you do the homework?
Yeah, I'll get to that. I'll get to that because we actually have a couple of different options on how you're going to do the homework. So right now, I just want to show you where it is. Okay, so of course, if you have the physical textbook, you know where it is. If you don't, then you have to get into here, and then here are the exercises. So you would do, notice there's not any page numbers. That's what's important here, is that if you're going to use the online system, which most of you are, there's not a page number, okay? This isn't page 181. This is just the exercises for 3.5. That's what you want to be looking for. Now, you do want to follow the calendar, and you do want to do numbers 1, 5, 15, so on and so forth. So you would start out by doing number 1, and then number 5, and then 15, and so on and so forth. And there are answers to all the odds. So every odd problem here has answers. Any questions on where the homework is, how to get to it? Good. Okay, now as far as that, that's option 1. Okay, option 1 is that you are going to do the homework paper and pencil on your own, either using the textbook or just looking at the problems on this ebook. Your other option, and I'm going to leave it completely up to you, is to not use the ebook and instead use these assignments that I've already made, where you click on 3.5 and it's going to bring up the homework assignment, and you will work through the problems. You still have to, you still work through the problems, but then you put your answers into the system and it'll check whether or not it's right or wrong. And you can get feedback that way. I personally do not care which way you do your homework. And the reason is, and this I think it will address your question, Abe, was that I do not collect homework for a grade. Okay, it's not part of your grade. And there's a couple of reasons for that. Number 1, this is calculus 2, so everyone here should know that if you don't do your homework, then you're not going to do well, okay? And the second thing is that I've already provided all of the solutions to you, right? On video, me working out all the problems. So it really doesn't make a lot of sense to me to ask you to turn in work for things that I've already provided you answers for. So the homework is truly for you to learn. I mean, it really is for you to learn. And with those homework solution videos, you got to be real careful with these, because you can use these the wrong way, all right? So since I'm not collecting homework, you may just watch my homework solution videos, and you may just sit there and watch them and be like, yeah, I get it. Yeah, I could do that. I could do that. And you never are actually putting pencil to paper. And that's not the way you should do the homework solution videos. What you should be doing is trying the problem and then having the video kind of up at the same time, pause it, work a little through it, and then watch a little of the video, see if we're kind of both doing the same thing, and kind of use it more as a guide and a check and a reference check, as opposed to just viewing me doing problems. So does that make sense to everyone?
Yeah.
Yeah.
So as far as, say, if we have any problems, saying with identities, or not knowing how you went from step 4 to 5, we can always ask you in class, Professor, I had this problem on this number problem. I could not figure it out how you went from A to B, and that's when you can explain us, I guess.
Yeah. Every
that
class when we meet. Every time we meet, I'm gonna, start the class out with, are there any questions over homework or anything else? So I'll be happy to go through. Now, my homework solution videos, I think, are pretty thorough. Like anytime I use an identity, I'm gonna at least verbally say what it is I'm using, and I try and show as many steps as possible. But still, yes, that you will have that opportunity to ask those questions in class. And you asked, when should you do the homework? So if, like today, right, we are covering 3.5, and here's the homework assignment.
Mhm.
I am going to assume that the next time we meet, right, which will be Thursday, you will have completed that homework, okay? And that's the way it works for every single one of these. So you have to be a little careful here, because especially between Tuesday and Thursday, if we have something that we cover on Tuesday, I really am going to expect that you've done the work for it by Thursday, because this class, more than any math class you've probably ever taken, builds upon itself extremely fast. So, you know, the beginning, the stuff that we do in chapter 6, in the very beginning here of chapter 6, this stuff right here, 6.1, okay, this stuff right here, if you can't get that down, then you have no prayer in 6.3 and 6.4. Like, it's not happening, because you have to be able to do the stuff from 6.1, 6.2 in order to do the stuff later on. So everything relies upon the previous sections. So we don't have the luxury in a Cal 2 class of saying, oh, well, you know, I'll get to it this weekend, you know, when I get to it. I understand that a lot of you have jobs and you're busy, but my expectation of you is that whatever we cover, next time we meet, you will have at least attempted the homework, made an honest attempt at it.
Okay.
Okay. Let's talk a little bit about bonus. Okay, so I did mention in the orientation little video that one way to earn bonus in this class is to stream your video while we're in these Zoom sessions. So right now I've got 11 videos up, and there are 22 people in the class. So what I want to see is, I want to be able to look up, and I want this to feel like a classroom as much as possible. I know this is difficult for all of us to adjust to this sort of learning style, but you know, I miss being able to turn around in my class and you know, see everyone and talk. Last thing I want to do is look up and just see a bunch of names and no videos, because then I really wonder sometimes if I'm just like talking to myself or not. So, and then what I'm going to do is, you know, we have a record of all these sessions are being recorded. So I'll be able to go back and look and see, like, were you consistently streaming your video? You don't have to do it every time. You can step away. It's okay. I'm not going to penalize you for one day not showing your video. It's just, in general, I want to look up and be able to see a majority of your faces. So, and another thing I'm going to do is, I have another screen over here, and I have all of your names, and I'm going to have my computer randomly shuffle your names every day. And so as I'm going through something, if I get to a point where I feel like I want to turn around and look at the class and ask a question, I'm just going to look up, and I'm going to look at there, and I'm going to say, hey, Joseph. Where's Joseph? Is he here? Where's Joseph?
Right here.
Where are you? Oh, there you are, Joseph. Yeah, I had to find you. Okay. So I may call on Joseph and ask him, hey, you know, what do you think about the next step? What should we do? And so that I'm going to consider to be participation. And every time that I do that, I call on Joseph, I'm just going to mark over here that he participated. And that's going to be considered, that's what I will look at the end of the semester when we're talking about bonus, or you're asking, like, what can I do to improve my grade? I'm just going to say, hey, I got to go back and look. Were you always participating? When I called on you, were you there? Right? Because inevitably it's going to happen. I'm going to call on somebody, like, I don't know, someone, right? And they're going to just not answer ever. And they're actually out, you know, they were over in another part of their house doing something else, which is fine. And I've been in plenty of Zoom meetings already where I disappeared into the other room, you know? So I know it happens, but I'm going to try and keep everybody honest. And most important, I'm going to try and keep you engaged. You know, that's the thing. We have to find a way to keep each other engaged in this. And that way, this will be somewhat enjoyable. Somewhat. Okay. Am I making sense? You're good.
Yes, but I have a question as well as CJ in the chat. We both have problems. Either doesn't have a webcam. And I have a camera on my laptop, but it's broken.
Okay.
Is there any other way that we can help, like interacting, or like say with
Okay,
this, I can use
yeah.
a mic?
So here's what I would recommend. If you don't have a camera, you're going to have one for the exams. So the college will actually give you a laptop. They'll loan you a laptop. So that's one option. It would be like a curbside pickup thing that you do, and they deliver it to your car, and you know it's yours. I would have to look into what you need to do that. And then the other option is, I'm assuming most people have a phone with a camera. You can download Zoom to your phone and just use that as your camera and just have that set up somewhere next to you. Does that sound like two reasonable options?
Yes, thank you.
Okay, okay. Yeah, so like I have Zoom on my phone, so I could right now, I could log into this meeting if I had the password and stuff, and I'd have two feeds in here. I'd have my camera here and I'd have another one over here. So I only need one camera from you, all right? But, okay, there was another question I thought, no? Okay, I was gonna say something. I've lost my train of thought already. Oh, interrupting me while I'm talking, while I'm lecturing. Because we are in this environment, I need you, if you have a question, I need you to just interrupt me, okay? Because it's hard to raise your hand, and so just unmute yourself and just, hey, hold up, you know, I've got a question, you know? Don't worry about that. That's what I'm gonna need from you. All right, so now in our course main Canvas page, if I can ever get back to it, there is also a link to our course files. And within files, there's a bunch of stuff. All the notes that I'm going to go over throughout the semester, I don't have notes for every section, but I have them for a lot. And the reason why I don't have them for every section is because there are some sections that I just like to start with a blank piece of paper and just let my mind go wherever it wants to go with that idea. So some things are like, we're going to just follow the notes. Other things we're not. So I invite you to print those out if you can, you know, so you can follow along. But while I'm doing my notes, I'll always have them up here, and I'll at least reference them while I'm going through them, all right? Now, formula sheets. This is something that you need to print out, okay? And you can have the formula sheets. You can have, let me go into this formula sheets thing. These are the formulas that you are allowed to have on every exam. But there's a little bit of a catch to this. You can only have them in a hard copy form. So you cannot be, during a test, looking at your computer to reference these formulas, which means between now and the first exam, you need to get hard copies. So how are you going to do that? I don't know. It depends on you. Some of you have printers, good. I know that there's print services now where you can send files and they'll print them like at Office Max and place like that. It's not that expensive to print out, you know, 20 pages worth of formulas. But I'm going to leave that to you, all right? And the formulas look like this. So there's a lot, for Cal 2, there's lots of formulas. You have, I believe, 6 pages, which come from the back of the book. And these pages are just formulas from pre-cal and college algebra, and there's geometry stuff here. So it's good for you to know what's here because you're allowed to have that on the test, right? So know where the things are when you need them. We also have this trig subformulas. We'll get into that in chapter 6. You'll be grateful to have that in front of you. And then when we get to chapter 8 later in the semester, you will really be happy to have this, because this is going to be a reference that you can use during the test to do your convergence tests. And then there's a last thing, which is a Maclaurin series table, which is, again, useful for chapter 8. So the sooner you can get all that printed out, the better. If you feel like, or if you find yourself in a situation where you just think there's no way you're ever going to be able to print that out, please contact me, and maybe I'll find some way to get you a copy somehow. Okay? Any questions on the formulas? All right. Any questions on anything else?
Yes.
I feel like I'm ready to start talking about stuff other than this.
Other than a thank you, no.
Okay.
Are we gonna do
Crazy.
reviews prior the exams, or that's totally?
Yeah, good question. I will give you some sort of review. Now, it may not be the type of review that you want, but it will be some sort of guidance as to what to study for. In a Cal 2 class, I really do kind of separate. I don't like to give, like, here's a review with 15 problems, go do these problems, and then, like, that's the review. I'm more of like a concept person, where I like to tell you what's going to be on the exam, how many of each type of problem you're going to have, but I really like to leave it open-ended, because as soon as I give a review that has problems, everybody gets tunnel vision. It just becomes, I'm only going to focus my studying on these things. And in a class like this, you can't have a narrow field of view. You have to have a very broad kind of, you got to be ready for all sorts of different types of problems. And yeah, I think I'm making sense.
All right.
But there will be something. I'm not just going to throw you right into it. What are the weights for the exams? I forgot. Let's take a look real quick.
All 22 and then 29% for the last one, and
Is
then
that
5% for your quizzes. Pretty sure it's what it was.
Okay, yeah, good.
Yeah.
So there we go. Now, so there is an opportunity here for quiz, and that will take form. You know, the quizzes can be in any sort of form. I mean, I don't know. I may just be like, let's take a poll question. I may do breakout rooms where I can take you and put you in like groups of 4 in different rooms in Zoom. And then from there, I can give you a problem to work on, and then I'll just go into the room and see if you got the right answer. And that's just kind of a 5 points that we'll just figure it out how we're going to do it. All right. Not quite sure exactly. It's just so hard to collect work from you.
Yep.
I had a question.
How many quizzes? Sorry.
No, you're fine. Go ahead.
How many quizzes will there be?
I have no idea. Hopefully more than 5.
Hopefully.
Hopefully more than 5, yeah. 5 maybe, because then they'll each be worth 1 point. I really put that in there because I wanted you to be able to get, it's almost like a 5 point, like I'm helping you. As long as you're here and you're participating, you know, then that 5 points, you should be able to get that. I just didn't want it to all be exams. All right.
Sir, I had another question.
Yeah, there was another question. Yeah.
Yeah, I was wondering if you could like get into detail about like your grading style, like in the tests, because I know that some math professors like if you like get most of the thing right, like they'll give you partial credit, but like if the answer is wrong, they take off points. How's that going to work?
That's a really good question. I don't think I've had anyone ask me that before. So you have to turn in, for all the exams, you have to turn in your work. Your handwritten work has to be, you know, pictures or scans, and you have to send it to me in a PDF file. Then I'm going to open that up, and I'm going to go through each problem. I'm going to be looking for correct methods and procedures, and be looking for correct notation. In a class like this, it's very easy for me to be able to tell whether or not you have any idea of what you're doing or not. You know, it's very early in the problem, I can know whether or not your train is on the tracks. And then from there, you know, whether or not you have little minor mistakes or not, I will always give partial credit. Okay, I mean, I'm looking for that because this is not multiple choice, right? It's not right or wrong. There's always this subjectiveness to the grading. And I think that I am a pretty lenient, fair grader as long as your work is neat, thorough, and logical, you know?
Okay, sir. Thank you.
Yep.
Okay, I had a question.
Yep.
Just thought I'd ask, what is your policy on calculators?
So I allow any calculator except the CAS. Do I have that in here? I don't think I put it in here.
Yeah, I didn't see anything like that.
I took it out because we had to put a different thing in here. So historically, I don't allow computer algebra systems. So anything that can do derivatives and things like that. But I also don't want people to have to go buy a whole new calculator for that. So your work, right? I'm looking for your work to be correct. So with these computer algebra system calculators, you can get the right answers without any work. That won't get you any credit on a test. So I think for what we're doing, I'm not going to have any real restrictions. So let's just say if you're going to use a computer algebra system, then that's fine, but your work better support it, because I'll be kind of pissed off if you got a bunch of right answers and no work, because then I know what you're doing. You know, now I know you're not even trying to think. You're just using the machine to do it for you. So does that sound fair?
So like we could use GeoGebra to like graph a function. That's
Not during a test.
not during a test, but like.
Oh yeah. Like, yeah, when you, I mean, we want to use the technology that's here for sure, right? It's just when you're being tested, I want to make sure that what you're doing is coming from here, right? Yeah.
Oh, and one other thing, can you define neat? Because I have terrible handwriting.
Okay, so neat means that your handwriting is going to be better at the end of the semester than it is right now. So if your handwriting is not neat, you're going to have to work on it. And I'm only saying this not because I really like it bothers me that people have bad handwriting. Like it's a matter of like, what's your major, Cameron?
Engineering.
Okay, so what kind of engineering?
Mechanical.
Mechanical. Okay, so do you think at some point in your life you're going to have to work with some other people on projects?
Yes.
Do you think that you're going to need to share some of your ideas and work with them?
Yeah, but I assumed by then it would be mostly computerized.
Okay, maybe, but you don't think you might be sitting, talking to a colleague over lunch or something and want to be able to kind of jot some things down and maybe just throw it on their desk for them to look at, or, I mean, it's a matter of communication, right? It's like if you ever need to communicate your ideas to another person, you want to be able to do it in a legible way. And it's not even like, I'm saying you have to have like periods at the end of sentences, but it should be neat enough that someone can follow it, right? And that's all I want. I just want you to work on that, because you are presenting your work to me, right? So I need to be able to read that. And so if you have bad, penmanship, math penmanship, it's something to work on, right? Something that you can improve on. That's all.
All right.
I have a question regarding calculator as well. So do you need any specific type? Like, for example, can we use the Casio scientific calculator, or do we need to get a graphing calculator?
You do not need a graphing calculator for this class. You do not.
Okay.
Now, it might help you in some sections to check a few things when you're graphing functions, but most of the functions that we graph are things that you should be familiar with: quadratics, trig functions, your basic trig functions. So you should be familiar with them, but if you have a graph calculator, you could at least check that. Like, we're going to need to find where some functions might intersect. And so maybe you could use your calculator, graphing calculator, to verify that point, but you should be able to do it algebraically. And I'm going to be looking to see that you do it algebraically.
So if I even do it with the graphing calculator, I wouldn't get a credit until and unless I show you how I got that point.
it would depend on the complexity of the problem, but if it's not obvious where these two functions might intersect and you all of a sudden just have an answer with no work, then that would not be considered full credit because I want to see you figure out that intersection point.
Okay, thank you.
Mhm.
I had a question.
Yes.
This was regarding homework, but currently I'm looking at the student assignments in the textbook, but I have no idea where to submit work. I know we will use Dropbox for exams, but when it comes to homework, I was wondering if you wanted our actual work that we did on the problem and where to turn that in.
Did I state that already?
Kind of. You said that
You did, yeah.
weren't going
You
to
don't take homework.
So
Yeah, I'm not
okay.
collecting homework.
Okay, never mind.
great.
Yeah, no, I just want to make sure. I thought I said it. You'll have to excuse me because I have two calculus 2 classes, one on Monday, Wednesday, one on Tuesday, Thursday. So sometimes in my mind, I may think I said something when I didn't. So no, homework is not collected because the solutions are out there, right? So the only things you're going to have to worry about ever submitting to me are the exams and any quizzes that I might ask you to submit.
Okay, thank you for verifying.
Yeah. And when we actually have to submit something to me, we're going to practice, okay? So like maybe next class, I'm going to give everyone an assignment to submit something to me. In fact, I've already opened up a Dropbox for you to practice. And I think some of you have done it. So let's see. I'm gonna open up. So for Cal 2, Tuesday, Thursday, I've had one person submit something to me as a practice. Let's see, do you mind me opening this? How do I say this? Right.
Yes, fine. I didn't know how to. I just typed something and then I saved it as a PDF and then I just submitted.
Okay, so I can open this. This is okay.
Yeah, that's fine. It doesn't have anything in there really.
Let's see if this is right. Okay, so yeah, all right. So there's just a single page here. So you did something right. It's a PDF file. What the thing that's going to be a challenge for people is to figure out how to send me one file with multiple pages. So let me go back. I'm going to show you an example of what I mean. I'm going to go look at my other classes. Let's see. My Monday, Wednesday class, I've had 4 people submit. Let's see if they got this right. So let's see. This is a single PDF file that was sent to me yesterday. Let's open it. It's 2 pages. Good. Let me zoom out. Okay, so the first page and the second page. Perfect. One file, 2 pages. That's what everyone needs to figure out how to do. And it's going to be different for everyone. Some people have iPhones, some people have Android, some people have scanners. But between now and exam 1, we got to figure this. You got to figure that out.
Yeah, I had a question. I'm using an iPad as my notebook, but
Yep.
whenever I'm taking a test, I can open an empty page and turn off the Wi-Fi's. Will that be okay to use my iPad? Because it is easier to send a PDF file straight from my iPad.
I understand what you're asking me. You want to write on your iPad during the test?
Yes. I can show my app that I'm using and take out everything that was there so that I don't go any other websites or any other places. Because I use that for my calculus one and my teacher was fine with it. I can show the webcam before I start the test.
No, I understand. Let me think about it, okay? And the only reason is because it just creates another element of something I need to do that is different for you, but everyone else has to do something different. So it's about being fair and having an exception for one person. And I just want to be fair to everyone. So if everyone else is writing paper and pencil, like everyone should write paper and pencil.
Okay, got it.
There might be a way we can do a workaround, but I don't know. Let me think about it. Let me
Okay.
consider. Yeah. Anything else? I like it. You'll have lots of questions. This is good. Okay, well, if you think of something, just let me know. Let's talk about calculus. So I'm not going to jump right into 3.5. We're going to talk about calculus for a little while. And I want to start by talking about calculus 1. Cal 1. So let's discuss this. What would you say are the main ideas in Cal 1?
Limits of a function.
Differentiation.
Derivatives.
Okay, limits. What else?
Derivatives.
Derivatives. Yeah. Okay. What were some of the things in Cal 1 that you found to be a little bit troubling, a little bit of a struggle?
The problem solving, optimization, and problem solving.
Optimization. A farmer has 300 feet of fence. He wishes to build a pen, blah, 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 right?
Mm-hmm.
What were those other ones that were like a spherical balloon is growing so that its radius is increasing at blah, blah, blah.
Yeah, it was like a rate of something.
Yeah,
And all
Related rates.
Related rates. Yeah.
related rates. Right? Related rates. I'm going to go ahead and circle these in red because I think these are always problematic. They're word problems. So they always seem to cause issues. All right. When it came to, what else? Is there anything else? Like, I think
Newton's method.
We
The what?
did max and mins with critical numbers on
Yep.
open and closed intervals, and then integrated that with like curve sketching.
Yeah, curve sketching.
Okay, so I think max min would be tied into optimization, which is also tied into curve sketching. How many of you covered this?
Hospital, yeah.
Oh, I did.
Okay.
We did.
I'm going to do a poll. This is very important. I'm going to do a poll on this one. So I'd like to know whether or not you covered L'Hopital's rule in Cal 1.
I think we did, but I don't remember.
If you don't know, then just say no. Wow, that's a surprising results right there. Okay, so let me show you what we got here. That's pretty surprising, actually.
Why is that
The other class
surprising?
was about 50-50 on that. So L'Hopital's rule is something that is covered by some Cal 1 professors, and others for some reason don't cover it. I always cover it in Cal 1. We need it in Cal 2. Like, we are going to need this rule. It's going to pop up in different places. So, you know, one thing you can do if you haven't seen L'Hopital's rule, or if you want to go back and review it, I'm going to show you what you can do here. When you go to our homepage and you go to my homework solution videos, when you're here, click on my username, okay? And that'll just take you to my YouTube channel. And then on my channel, you will see I've got Cal 1, Cal 2, Cal 3. Those are my top 3 things here. And if you go to Cal 1 and look at my course videos or class videos, you can do both of these. You click on that and then scroll down here. Let me mute this and pause it. Okay. You scroll down here, you'll see something here on Where is it? Where the heck is it? I think it's 2.7, but let me go to the course videos real quick.
Yeah, first.
Okay. Where the heck is it? My goodness, I was just here the other day. Oh, here it is, 3.7. Indeterminate forms and L'Hopital's rule. Okay. So what I'm saying is that if there's anything from Cal 1 that you feel like maybe you need to go back and look at, I do have some videos out here that you could use. All right. All right. So what is the derivative then? Like, what did we learn the derivative is in Cal 1?
The instantaneous rate of change, the tangent of a line at a point, oh yeah, the limit of the difference quotient, and there was one more, but I forgot what that one was.
I think you've pretty much nailed it pretty good there. Geometrically in Cal 1, what it all really came down to, okay, in Cal 1 was this. If we have a function, so when we say a function, we mean a function of x, meaning that it is a curve that passes the vertical line test, right? As long as it passes the vertical line test, we are talking about a function of x. So in Cal 1, we learned that if you have a function of x and you pick some arbitrary point, let's say a, on that on the x-axis, which would be in the domain of the function, and you evaluate that function at that point, of course, you're going to have whatever that value is the value of the function at a. So that's how high that point is. But in Cal 1, we were more interested in finding the slope of that tangent line at that point. So the slope of that line would be equal to the derivative of that function evaluated at that point A. So yeah, the derivative gives you information about the instantaneous rate of change of a function at some given value, whether it be at A or at X or at whatever you want to call this. This is a kind of a dummy input. But the derivative of a function was just a new function, right? That's all it was. You start with a function, you take its derivative, you get a new function. And we use that in very clever ways in Cal 1 because we said, all right, if we have somewhat complicated looking functions and we want to have some information about where these functions might reach their peaks and valleys, right? Minimums and maximums, then we realized that those points correspond to where tangent lines are potentially zero. And so anywhere where we had a derivative that was equal to 0, that would be a place we would go look to try and find maximums and minimums. So it really helped us kind of formulate this idea of optimization where we could find maxes and mins. And I'm kind of simplifying it because there's different ways to find max and mins, and you can have places where you have cusps and you can still have a maximum there. So I'm kind of oversimplifying it, but the general idea in Cal 1 was give me a function, I'll use the derivative to be able to determine the shape of it, highest and lowest points. And then we use that to answer other questions. All right. I think that that's a decent kind of overview right now of Cal 1. What about Cal 2? First of all, what have you heard about it? Have you heard anything about Cal 2?
Antiderivative.
We got into it a little bit at the end of Cal 1, but not much, but antiderivatives.
So you've heard about these things called antiderivatives.
Oh, integrals, that's what it was, yeah.
Okay, antiderivatives. And then you've heard something called integrals.
My mother always says series.
Series, yeah.
And I think area under the curve.
area under the curve. Yeah, these are all topics in Cal 2. Antiderivatives, integral. I circled series in red. Because remember we circled some stuff in red here earlier? From Cal 1, these were kind of the things that people didn't really enjoy, kind of struggle with. Well, here's what I'm going to say about this. I think when you get to series, you're probably going to wish you were doing optimization and related rates again. Like that's what you're going to kind of wish you were doing, because series always gets people. I mean, it's just, if you've never seen series before, it's the newness of it and it's the strangeness of it that you're just like, whoa, okay, there's a lot going on here. All right, this is good. Now, what have you heard about the class? Like, other than topics, what have you heard about the class, like Cal 2?
That it's like the hardest of the calculus classes.
Heard it's hard?
I think it was easier. My friend said that it was easier than Cal 1.
I've heard mixed things like that too from multiple people.
I've
I've heard that
you gotta-
calculus 2 is harder than 3 and 1.
Yeah. So it's my opinion that Cal 2 is the hardest in the sequence. If you do Cal 1, 2, and 3, I've heard, my feeling is that 2 is the hardest. Now, sometimes you find people who, they think Cal 1's harder or whatever, and that could just vary from, different professors or something like that. But I think when you take a realistic look at things, there's something fundamentally different in Cal 1 and Cal 2. And you're going to discover this very quickly. In Cal 1, everything is mechanical. Everything is a formula. Everything is a process. Everything is a procedure. Think about it, right? Limits, right? Well, yeah, limits sucked because what made limits suck? What part of limits made limits suck? The algebra, right? All the complex algebra that was involved in the limits. You would have to rationalize numerator and denominator. You have to do some factoring. But other than that, yeah, of course there's other problems, but there was a procedure. You take the derivative, there's a difference quotient, very mechanical, follow the formula. You learn the power rule, right? Take the derivative, you bring the power down, subtract 1, right? Very mechanical. Then you get to Cal 2 and it's not as mechanical. Everything, it's more of an intuition you have to have. And the intuition comes from your comfort with the Cal 1. So if you are really comfortable with product rule, quotient rule, chain rule, if all of those mechanics made sense to you in Cal 1 and you became proficient with them, then it's going to be a lot easier to do what we're doing, because there's just this intuition you have, and it's very difficult for me to teach that intuition. So you'll see that. I mean, I'm going to teach you different approaches and methods, but every problem that you're presented with is going to be uniquely different. And so you're going to have to have this new sort of willingness to fail. Like, you're going to have to be willing to try to do a problem and invest 30 minutes into it, and then realize that you're just completely going down the wrong path, and crumble it up and start over, and just kind of keep throwing yourself at it. And then as you do that and stay persistent, you will start to make breakthroughs. All right. So I feel like your bar, like what you think your limit is as to how high, the level of thinking you have, after Cal 2, that level goes up. Now, I will say that I think the material in Cal 3 is just as difficult. But the thing is, Cal 2 hardens you. Like, you're a different math person when you come out of Cal 2. So when you get to Cal 3, you're just more prepared for the level of difficulty. That's my opinion. That's my take. I've only been teaching this for, I don't know, I'm going on 20 years right now. So I have some experience with this. That's my opinion. Now, you can do this, all right? You can do this. Cal 2 can be done, but you have to be able to look at yourself in the mirror and say, I am putting in the time and effort. Okay, you have to be able to do that, because there are some people who get through Cal 1 and it doesn't require a lot from them. You know, I remember being in Cal 1, and I had a couple of classmates, and it's like, all they had to do is show up, they'd watch the professor, they're like, yeah, I got it, they could do it. And I was just like, man, how do they do that? And then we get to Cal 2, and it didn't work for them anymore. Like, they had to go in and practice, and they weren't used to it. So, gonna get your hands dirty.
Sir, I have a question.
Yep.
So in your opinion, what are the concepts from Calculus 1 that are most going to be applied in Calculus 2? Because I heard you say, like, if you're familiar with the product rule, chain rule, and quotient rule,
Yep.
are those going to be are we going to use those a lot?
Yeah,
in
we'll use
Calculus
those
2?
all the time. We'll be taking derivatives. Derivatives will be happening all the time, and they'll just be an intermediate step within a bigger problem. So, you know, yeah, so derivatives, I mean, this class makes you go back to everything. Like, you've got to be able to pull from pre-cal, you got to be able to pull from college algebra, you know, so there's stuff like, oh, okay, you know, let's look at sine function, and, you know, where's, I mean, it's just all the trig identities from pre-cal, they're all on the table here, you know, double angle identities, power reducing formulas, everything is here. Now, it might take us like a minute when we're going through problems, it might take us a little bit to be like, oh, remember this? Let's go back and look at, okay, yeah, here, we're gonna need it, you know? And I know it's gonna take you kind of flipping back through your memory, but like, really there's no kind of limit as to how far we can go back and how much we'll need. There's a little bit from everywhere.
Professor?
Yes.
So does that mean we'll be sort of memorizing, for example, the integral of cotangent x dx is also ln absolute value of sine x plus c.
Mm-hmm.
No,
you won't memorize that because you have that on a formula sheet.
Okay. And what about the fundamental values of the fundamental theorems of calculus? Will those also be on a sheet, or?
No, you'll know that. You'll have
Okay.
that memorized.
Okay.
Yeah, I mean, it'll be kind of like, you know, you're not going to be able to get up and walk without putting your shoes on, and that formula will be like your shoes. Like, that's a terrible analogy, but you know what I mean? Like,
Yes.
right now it may seem like it's something you have to memorize, but you're going to use it so much that it's just going to be there.
Okay.
You know?
Okay.
Yeah, I am
Thank you.
personally not a big memory person. Like, I'm not one of those people who, like, I can memorize all these different formulas. When I was in Cal 2, I had to memorize all these things. Like this right here that I showed you earlier, I had to memorize this. I had to know all these tests when I took my exams. I had to know those. And I had to know this. And I had to know this, you know? But there's different philosophies when it comes to this whole idea, you know, of memorization of formulas. And my philosophy is that in the real world, right? In the real world, you're never going to be trapped in a room by yourself with no resources, right? I mean, Cameron, you want to be an engineer, right? You said?
Yes.
I said, you're going to maybe have to communicate with your colleagues, but you're never going to be just completely isolated with nothing, right? And you're like, oh crap, what's that formula I needed? Like, you're always going to be able to go and grab something. The most important thing that you can get out of a class like this is, and maybe I should just pause for a second because this is so important. To me, it doesn't have a lot to do with what we're learning here in terms of, oh, you're going to learn how to do integration. You're going to learn how to find areas. You're going to learn how to do series. To me, it's not about that. It's about you becoming a problem solver. That's what it's about. It's about whether or not you're the type of person, when faced with a difficult problem, are you going to continue to, is it going to bother you? Are you going to lose sleep because you can't figure this out? Or are you just going to kind of curl up in a ball and just submit? Because that's what a degree in engineering, computer science, all of it is about. It's about coming out of the other end, you being like so hardened that when you go to get that job, they know, like, they know when they give you the task that you're going to get it done. You know, that's what this to me is all about. Problem solvers. I'll give you an example. So my brother is an electrical engineer. All right. He went to Boston University. He did electrical engineering there. And then he went over to Georgia Tech and got his graduate degree from Georgia Tech. He works in Austin for a company that I won't mention. So his interview, right? His interview, they asked him some questions, but there were two questions in particular that they asked him. And here's the first one, okay? The first one they asked was, you ready for this? This is an interview question. They said, you've got 10 coins, okay? 10 coins. They're all identical. But you look at them, they all look exactly the same. But one of the 10 weighs just a little bit more than the others. Okay, so 9 of them have the same weight. 10th one is a little bit heavier, but you can't distinguish them. You can't like feel it in your hand and tell. And then you're given a balance. Okay, so you're given like a little balance, little teeter-totter balance. Okay, so you've got the 10 coins, you've got the balance, the little teeter-totter balance. What is the minimum number of weighings that you would have to do to guarantee me you could find the coin, the heavier coin? I'll restate the question. So you've got this little balance, you've got 10 coins, they all look the same. One of them is heavier. What is the minimum number of weighings, or if we're going to call them weighings? That would be if you put any coins on the scale, that would be a weighing. What's the minimum number of weighings that it would take to guarantee me you would find the coin?
That would be 4.
Okay, 4.
True.
3.
I want to say like 81, 100, something like that.
Okay. All right, so the correct answer is 3. So how would you do it?
You would split the coins in half,
Okay.
5 and 5. Whichever
five over
5
here and
weighs the
5 over here.
heaviest
Okay.
means one of those 5 on the heavier side is one of the heavier coins.
Okay, so let's say the heavier coins were over here. Okay.
Yeah.
All right, so we're gonna row these out. Now that's one weighing. Now what?
Now you split those 5 coins. Just take 2 and 2.
Okay.
And then if both of them weigh the same, then that means you just have the heavy coin on the side.
So when you put the 2 and 2, if that balances, then that's your heavier coin.
Yes. So it could be 2 or 3. But if one of those sides weighs more, then one of those 2 coins is
That's
the
right.
heavier one.
You're guaranteed to find it that way.
Yes.
Guaranteed, right? And that was, I didn't count the second one, but that would be the third weighing. 3 is the minimum to guarantee you would find it. Now, could you get lucky and have found it on the first one? Like, let's say let's say you just took a coin here and a coin here, and then you put the other 8 over here, and then you weighed them, and this side went down, right? You got lucky, right? That's what that would mean. You got lucky. That's not what the question was. The question was, what's the minimum number to guarantee you would find it? Okay, that was the first question on the interview, or the first question they asked them. All right, you ready for the next one?
Just
All right,
out
the
of
next
curiosity,
one-
did he answer it?
Yeah, you got it.
Okay.
Okay, the next one is, now you have to pay attention because this is a word. I'm not going to write anything down, so you have to pay attention to the question. 2 archaeologists walk by a cave. One of the archaeologists goes into the cave, comes back out several minutes later, and tells the other archaeologist that they just found the perfectly preserved remains of the first human being ever. How did they know they had found the first human being ever? I'll restate the question in a minute, but I want to give someone an opportunity to answer.
They walked really far into the cave.
Okay.
Because they're archaeologists. They know that stuff.
Anyone else? I'll repeat the question. Two archaeologists walk by a cave. One of them goes in, comes out after a little while, tells the other one, I just found the perfectly preserved remains of the first human being ever.
Oh,
How did they know they had found the first human being ever?
I changed my mind. It would be like, well, the preserved human being would be like super hairy and very ape-like. And if it's perfectly preserved, you'd be able to tell, yeah, that's really old.
Okay. Anyone else?
I was gonna say their features.
What do you think? Wait, I'm sorry, I didn't hear that.
I was gonna say their features, maybe.
So what do you think like the key words to this problem are?
Perfectly
human being.
preserved.
Perfectly preserved. Those are the key, that means something here.
Is it because that the human being that was found was preserved and they had enough evidence to say that?
He was frozen?
Well, he was preserved, or it was preserved. So preserved should imply that the entire person was there, right? Like every detail of that person was able
Yes.
to be assessed.
Exactly. I think that's the only reason, because the whole person was preserved.
Do you want the answer or one more time?
He was frozen? In ice? Something?
Something, yeah. The problem doesn't state how it was preserved, but that it was perfectly preserved. All right, you ready? Because we got to move on. We can't be on this too long. Yes?
Okay.
So the preserved person that the archaeologists saw didn't have a belly button.
Mm-hmm. That doesn't make sense.
Oh, okay.
No, it does. It makes sense because umbilical cord. That's right.
Well,
If you don't have a belly, you only have a belly button if you were born, right?
well, yeah. But okay, never mind. That gets into evolution.
Found an alien.
It's very clever.
Okay, so look, I mean, I didn't make up the question. That was an interview question for a job, for an electrical engineer. Do you think that has anything to do with all the math and engineering that my brother had worked on his whole life?
No.
That had to do with problem solving. That had to do with analyzing that question, every little aspect of it, and reaching a conclusion under pressure and having a reasonable response, right? And he got it. So I think you only get that by training your brain to think a certain way, you know? And some of you may not like the answer, but that's the answer they wanted. There's also another answer that the human with the preserved remains was missing a rib, but that's more of a kind of a religious sort of, like Adam and Eve, Adam was missing a rib, something like that. But that's not the answer they wanted. They wanted the missing the belly button thing. So anyway, what's my point? I was trying to tell you when this all started that a course like this has a lot less to do with the actual math to me. I mean, of course, I'm going to make sure you can do the math, but what I want is for all of you to raise your level of problem solving and get to a point where you didn't even know you were capable of so much suffering. You know what I'm saying? Like you were able to get through things that you didn't think you could get through. Okay. That's fun. I feel like I'm missing something. Oh, yeah, I wasn't done talking about what Cal 2 is about. Okay, so let me give you just a real general kind of rundown of what you should expect in Cal 2 in terms of the things we're going to do. So the first part of the course, the first 1/3 of the course, we're going to be doing antiderivatives. And what that means is that we're going to look at a function and we're going to say, hey, that function is the derivative of something. What is it the derivative of? So, I mean, I could give you this example. If I told you, look at this function, f of x equals 2x. That function is the derivative of what?
X squared.
X squared.
Right? Yeah, so if I said capital F of x is equal to x squared, then I hope that everyone would then agree that that this thing up here would be equal to the derivative of that. So if I take derivative of this, I get that, right?
Wouldn't it be x squared plus c?
Well, yes, that would be the general antiderivative, but just x squared by itself is an antiderivative.
Yeah.
There's an infinite number of them because you could always throw a number onto that, any number you want, and it would still qualify. But all I'm trying to get everyone to see right now is that antiderivatives have to do with starting with this end and trying to go backwards to this one, which seems like it could be somewhat straightforward in the beginning, but then you try something like this. So let's start with this end. If we said, take this function, sine cubed of the square root of x plus e to the x, right there. Right, there's a function. I'd like for us to take the derivative of that right now. We're going to take its derivative. So this would be a Cal 1 thing. So I've got chain rule, right? Does anyone want to show off their differentiation skills and tell me what this derivative is? So derivatives of compositions of functions is like working on an onion. You start at the outer layer and work your way in. So what is the outer layer of this onion? What is the outside function? What's the last
Sine.
operation you happen?
The sine.
Is it the sine or is it the cubed?
Cubed.
I think cube.
It's the cube. That cubed is the last operation to happen. So when we do our derivative, we have to treat this almost like a power. We have to bring the 3 out. Sine squared, square root x plus e to the x. I'm not showing the work. This is something hopefully you could do given enough time. We're not done though, right?
No.
Now what I would have to multiply by the derivative of the next layer in, which is the derivative of what?
The sine.
The sine function, which is cosine
Cosine square.
of this. And then I'd have to multiply that by, so I'm kind of like working my way in. That's gone, that's gone. Now I'm ready to take derivative of what's in here. So I can just do those individually.
So 1/2 x to negative 1/2 power plus e to the x.
Plus e to the x, because the derivative of e to the x is itself, right?
E to the x.
Yes, sir.
Yes.
Oh, I remember.
And while we're talking about this, I just want to tell everyone, because I'm going to do this a lot in this class, anytime you see the square root of x, if we take the derivative of it,
Just one
it
over
is
two.
1/2 x to the negative 1/2, but I'm always going to write it this way. It's the same exact expression. It's just that, to me, it's just faster and easier, and I don't like the negative exponents. So the derivative of the square root of x is 1/2 root x. This would not be wrong. I'm just not going to write it that way.
Okay.
Okay, so that's our derivative, right? So now we're in Cal 2. So what if I started with this? And I said, hey, that's the derivative of something. What is it the derivative of? Right? You got to somehow get that back up to this thing. And that's a little bit harder to do. It's a little bit harder. In fact, it's going to be a lot a bit harder. Okay, it's going to be a lot hard. Okay, so that'll be the first third of the class. We're going to just be doing antiderivatives. And then after we do antiderivatives, the second third of the class is going to be applications. So we're going to say, okay, well, now that we can find antiderivatives, what are they useful for? Like, what's the value of being able to do an antiderivative? So I'll kind of remind you of something that you already did in Cal 1. Let's say in Cal 1, you had a function that you had time here and you had distance here. So this is back in Cal 1. Then if you found the slope of the tangent line, that would give you what?
Velocity?
Velocity, okay? It would be velocity. It would be speed. It would be the distance over time, okay? It would be that ratio. So we know that if you're given a position function in Cal 1, then by taking the derivative, you will get a new function, and this new function will be the velocity function. And if you take the derivative again, what would you get?
Acceleration.
Acceleration function. Well, guess what? If we can do antiderivatives and we go backwards, instead of going from right to left, we go left to right. So what that allows us to do is this. If we take a function, and let's say that this function is velocity. So in other words, this is velocity and this is time, or this is, you know, speed and velocity are not the same thing, but in this class right now, we'll just kind of act like it is. Let's say we have a velocity function and we find the antiderivative. What would the antiderivative of velocity be then?
Position.
Position. Right? Position. Well, it turns out what we're going to find is that if we look at our velocity function between 2 points, and we only focus on the curve between here and here, and we look at the velocity at every point in time, then the area underneath this curve, the area is equal to the total distance traveled. So if I know how fast something is going at every point in time, I can actually tell you how far it went so long as I can calculate the antiderivative. And this goes, and you start to have a lot of different applications you can do with this. It doesn't have to be velocity and time. It could be distance and force, and then your area would represent work. That's more of a physics application. And there's really no limitation as to what you can do. So it's going to be kind of cool. We're going to be able to find the areas under curves using the antiderivative. Another thing that we'll be able to do is take, let's say, take a semicircle. Let's just take the first quarter of a circle here. Let's say that the radius of this is r. Okay, so this is r, this is r, this is a quarter of a circle. In this class, we're actually going to be able to calculate the area underneath this, okay, using the antiderivative. And from that, we are actually going to be able to prove that the area of a circle is pi r squared. We're going to be able to prove that formula. We've always taken it on faith, right? It's been handed to us by someone else. But we're going to be able to use the antiderivative to prove that formula. And then we're going to do some crazy shit. We're going to take things like, we're going to imagine taking this picture right here. And we're going to imagine taking that little semicircle and just wrapping it around the x-axis. Just imagine it's 3-dimensional now and wrap it around the x-axis. So if I did that, do y'all see if I kind of wrap this around the x-axis? I would create like half of a sphere, right? We are actually going to be able to calculate the volume of that. So if you take any curve and start wrapping it around the x-axis, you can create this solid And then we can use the antiderivative to calculate the volume. And so we're actually going to be able to prove later that the volume of a ball is 4/3 pi r cubed. We'll be able to prove that later. But it's all going to rely on the antiderivative. And there's a bunch of other things we're going to do. We're going to be able to take a curve. You've probably never thought about this. Take a function like this. Imagine that you could take this function and take it off the page like it was a string, and then pull it tight and measure how long it is. That we call the arc length. We'll be able to measure how long any curve is on any function, the length of that function, which is very useful if you have something moving through space and you want to know how long that path is, right? And it's even more useful when you get to Cal 3 and your path can be in 3-dimensional space, because then you can talk about things that are moving around and you can figure out how long that path is. But we're going to stick with Cal 2 for now, arc length, right? And then we'll do
Sam's Club.
Pardon? Oh, I was telling my other class earlier today, it's inevitable that we're going to hear something or see something that we can't undo, you know? So we're all adults, right? I had a girl last semester who decided to take her test with just a t-shirt on and very little else, and then got up to use the restroom and forgot that she was on video with all her classmates, and I think that was quite embarrassing for her. So, you know, I think these things are inevitable. You know, your microphone's on, you know, I don't care. Let's just all be adults about it, right? We're all trying to learn. I hope I don't mess up. That's why I have this fake screen in the back so you can't see the chaos that's going on behind me. All right. Okay, so that's going to be the applications, about 1/3 of the stuff. All right. And then we get to the last third. And there's more applications. I'm kind of cutting it short because I've already talked so much. The last third is going to be series. And I have a good little introduction for series, just kind of a way to get you thinking. All right, so let's talk about this. Let's say that you have your calculator right now. If you have one, great, you can break it out. I want you to take sine of 1. And let's make sure you're in radian mode. Okay, so I'm going to get my little calculator out here. And I'm going to type sine of 1. And I get approximately 0.84147. And then it keeps going, but I'll just stop there. So maybe you've never thought about this, but what the heck just happened in here, right? Like, what just happened? This is a computer, right? All it understands are zeros and ones. That's all it knows. There's either an electrical signal or there's not, right? We know, and I think we can safely all be comfortable with the idea that computers can do arithmetic, right? Addition, subtraction, multiplication, and division. Those are operations that we should expect this can do. But when you talk about like sine of 1, do you think that this computer has any concept of a sine curve? Any relationship between this and the unit circle, right? Nothing, right? This gave us an answer of 0.84147 by doing simply arithmetic, addition, subtraction, multiplication, and division. So what did it do? Well, I'm going to show you what it did. It used a formula, which is pre-programmed into the calculator. And here's the formula it used. It used what's known as the Maclaurin series for sine. So I'm going to take a quick little snapshot of this. throw this in here real quick. So according to this formula that you are going to just take on faith at this point, and you're going to ignore all this, sine of x is just x minus x cubed over 3, what does
Factorial.
that mean?
Factorial.
3 factorial. So 3 factorial means 3 times 2 times 1. You don't need to put the 1, but I always put it. 5 factorial means 5 times 4 times 3 times 2 times 1. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. That factorial is used in statistics a lot. But so this is saying I'm going to take x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. So if I want to know what sine of 1 is, I'm just going to do 1 minus, what's 1 cubed? 1?
1.
1 over 3 times 2 times 1 plus, let's see, 1 to the 5th, which is 1, over 5 times 4 times 3 times 2 times 1, minus 1 to the 7th, which is 1, and then 7 times 6 times 5 times 4 times. Now, if you get on your calculator and you do that, it's just arithmetic. That's it, right? That's all that is, plus, minus. I promise you, if you do that, you're going to get a number that's pretty close to 0.84147. And if it's off a little bit, well, then you see this little dot, dot, dot? That little dot, dot, dot means that that pattern continues forever. So if you wanted to get more accurate, the next piece that you would have would be, well, what would it be? Would it be plus or minus?
Plus.
Plus
Looks like it would be plus, and then it would be
x to the
X to the
9th.
ninth.
x to the 9th, so it'd be 1 to the 9th power over 9 factorial. And then minus, if you wanted to get even more precise, you go to the next one, which would be x to the 11th over 11 factorial. And then if you want to keep going, 1 over 13 factorial, that would be plus. Do y'all see that?
Is there a reason it's all odd numbers? Yes.
That is
It's
a
a
wonderful
sequence.
question. Why is it all odd numbers?
There's a sequence.
This is, yeah, this is a pattern, right? We have this pattern. So there's a couple of natural questions that occur here. If you believe that this is true, okay, then you should have some natural questions. Number one should be, where the hell did it come from, right? Like, how do you come up with this? And the next question might be, why are they all odd, right? Why is every number in here x cubed over 3 factorial, x to the 5th over 5 factorial? Why are they all odd, right? So let me answer the first question. Where does it come from? It's called Taylor's formula. And it was a beautiful breakthrough that we will see. We're going to be able to do this. We're going to be able to derive that formula on our own, okay? And it turns out that every function out there, every function that you could ever really come up with in your life has this sort of what we call a power series. There is a power series representation of every function that you would ever really deal with in your life, which is great because then we can use computers to analyze functions, right? Y'all buying this? You have to take it on faith that it's possible, but, and now the second question, why is it odd, right? I think Cameron asked, why is it odd?
Mm-hmm.
And the answer is simply because that's the nature of it. That's the nature of this. In fact, weren't you taught in pre-cal that sine is an odd function? You were. And
Yep.
guess what? It doesn't have any, yes, it has to do with reflections over axes,
Mhm.
but really what it has to do with is the fact that its power series involves odd powers only. That's what makes an odd function odd. Cosine is an even function, right? Guess what its power series has in it?
Even numbers.
Evens only. Even, here's cosine. You see this? Look at all the powers on x. They're all even. What about e to the x? E to the x is not even or odd. It's neither. Look at its power series. It's got a mixture of evens and odds. So anytime your power series has a mixture, you have neither. it's just odds, you have an odd function. If it's just evens, you got an even function. That's pretty weird, huh? These are the common ones. Look at this one right here. We're gonna take this to the end. We're not gonna start anything new today. I didn't want to tell you that in the beginning because I wanted y'all to pay attention. But this one right here should blow your mind. All right. Look at e to the x. All right. Let's just take a look at what this is. All right. And you know what? I'll copy it over. Okay, that's what e to the x is, and we're going to ignore this for now. Okay, so if I wanted to know what e squared is, I would just replace all the x's with 2, right? But this is the part. I'm sorry, this is just no matter how long I've done this, I still get goosebumps when I do this shit because I just think this is so beautiful. Okay, I'm just going to write out the next few. Do y'all see the pattern? Okay.
Yep.
Now, from Cal 1, what is the derivative of e to the x?
E to the x.
E to the x.
So what I'm going to do right now is I'm going to take the derivative of this. Well, what's great about power series is that if you want to take the derivative, well, can you take the derivative of powers of x? Are you comfortable doing that from Cal 1?
Mm-hmm.
Yeah. Can you take a derivative of things that are being added and subtracted?
Yes.
Yeah, you like that because there's no product rule, no quotient rule, right? So let's just start taking derivative of this thing. What's the derivative of 1?
0.
0.
What's the derivative of this?
1.
1.
1 factorial is just 1, right? So derivative of
1
x
divided by 0.
plus. Okay, let's do this one right here. What's derivative of this? So the 2 comes out, right?
2 to the x over 2.
You'll have 2x over 2.
2.
Okay, let's look at the next one.
3x squared over.
I'm going to write it that way. Got it? Anyone see what's happening?
There's a pattern to this as well.
Let's start
You're just
cleaning
getting
this up.
closer and closer to that value.
Mm-hmm.
What is this turning into? This is 1 plus, what is this?
X.
2.
Okay, what's this? 3's cancel. What is that? X squared,
X squared over 2.
2 factorial plus, what do you get here?
X cubed
X
over
cubed over
6.
6.
3 factorial. I just got goosebumps. 5's cancel. X to the 4th over 4 factorial.
Oh,
That's
Insane.
so then if you take the derivative again, it's just gonna.
They're the same thing. It's the only function that does that. Only one. Freaking beautiful. Math is so beautiful sometimes. Look at this. Okay, let's go back to this one. What's the derivative of sine of x? We all know this from Cal 1. Derivative of sine of x is cosine x, right? We're all happy with that. Okay, let's take this derivative. Okay, so what would the derivative of x be?
0 or 1.
1.
Minus. Now, what would the derivative of this be?
3x
6 over 3.
1
Oh, it would.
plus 5x to the 4th over 5 times 4 times 3 times 2 times 1 minus 7x to the 6th over 7 times 6 times 5 times 4 times 3 times 2 times 1. Let's clean it up. 1 minus what?
X squared
over 2.
And it would be
Plus
x to the
x4 over 4.
Factorial. X to the 6 over 6 factorial.
And what is that?
Oh.
1 minus x squared over 2 factorial plus x to the 4th. Those are all even powers.
Oh,
Let's
it's
go back to our formulas.
Prove that, non-believers.
Look at cosine. That's what cosine is,
Oh, it's insane.
right? Power series are the way to go. Okay, when you get to computational math, computer science, power series are the way you want to work. That's the way you want to do arithmetic. Because the series, see, we all know that computers are finite, right? Like, we know that if you type in sine of 2 into a calculator, at some point it's going to cut off, right? It's going to take you out so many decimal points, and then at some point it has to stop. All it's doing is stopping somewhere in the power series. If you need more precision, you just go further out. Okay? And that's okay for what we do in this world. We can never be so precise that we would ever need the exact answer out a billion decimal places. If you're building aircraft ball bearings or something, right, you got to be pretty precise. But your power series can be as precise as you want them to be. Okay, so can you see, at least from this a little bit, that it might be worth it for us to understand how to take a function and generate its power series so that we can use it for something?
Yeah.
Yes, sir.
Okay,
That's
good.
Oh,
All right, well,
random question.
yeah.
Are we gonna ever encounter any of these series having 0 factorial or no?
Yes, 0 factorial will come up.
Okay.
So we may as well just talk about it right now. That 0 factorial, if you haven't seen this before, 0 factorial is, by definition, anytime we want to define something, we put a colon in front of the equal sign, is 1. Which doesn't make a lot of sense, but it is 1. And if anyone wants to have a discussion about that later, it makes perfect sense. Okay, so the best way that I can explain this whole idea right here to you right now is, and it's not a very good explanation, I just have to get you to believe that right now you live in a fishbowl. Okay, that's you in the fishbowl. And so when I'm telling you 0 factorial and you're like, that doesn't make any sense, it's because you don't understand, and you wouldn't be expected to understand as a fish on a bowl on a table, that there's an entire universe outside of your bowl that you don't understand yet. There's dogs running around, there's trees, you're a fish in a bowl, that's all you understand. So 0 factorial, right now I'm telling you it's 1, and it may not make any sense to you why it's 1, but trust me that there is a perfectly reasonable explanation as to why it's 1. But we have to define a new function that involves complex numbers. That's something that we do not deal with in this class. In fact, the entire sequence of calculus, if you look at most calculus books, it'll say in here, calculus of a single real variable, meaning that we have one variable and that variable is a real number. Once you start to involve complex numbers, imaginary numbers, then you no longer live in the fishbowl. And then the mathematics of 0 factorial would make sense. That's about all I can give you on that right now. We can discuss this further later. All right. Have any of you heard of the Riemann Zeta function? No? Okay, we'll definitely have to talk about that later. What are we doing now? So what is the task? What is your job between now and Thursday? I need you to just make sure that you go back, start getting yourself up to speed on derivatives, make sure that you feel comfortable, review your unit circle, trigonometric values at the common angles. So like when I come in here on Thursday and I'm like, yeah, we know that, cosine of pi over 4 is.
I hate trig.
Square root over 2. Square root over 2.
2 over 2.
Yeah, so you want to get to that point where you're, at least let's get those gears going again, all right? And then you have kind of like one day to take a breath and gear up and get mentally prepared. And then Thursday we start hitting the pavement running. All right?
So were you talking about Riemann sums?
Riemann sums, I didn't specifically say Riemann sums, but we will talk about Riemann sums.
with the positive and negative and okay. Yeah. Okay.
I said the Riemann zeta function.
Zeta. Okay.
The Riemann zeta function.
Definitely want to look into it.
Yeah, that now I will warn you, the Riemann zeta function has been studied for a very, very long time. It's an unsolved problem in mathematics. And if you could solve the Riemann zeta hypothesis, then you would become an instant celebrity. You would become a millionaire because it's one of the $1 million problems. Nobody's been able to prove the hypothesis, but no one's been able to disprove it either. But yeah, I don't want you to, don't bury yourself in the Riemann zeta function. You know, get yourself ready for this class. Okay.
Yes.
All right, everyone. Well, I enjoyed that. I hope you did, and I will see you all on Thursday.
Have a nice day, sir. Take care.
Yes, have a nice day. Thank you.
Have a good day.
You too.
Thank you.
Yes, sir.
Bye.
Thank you.